तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last class, we had looked at two stress measures. We call the first stress measure as the first Kirchhoff stress measure. Of course, this is apart from the Cauchy stress, you already know. The second is the Kirchhoff stress measure. Okay, remember that we developed a relationship between the Cauchy stress, the first PLR Kirchhoff stress, which can be written as sigma is equal to J inverse P F transpose, and this P which we called as the first PLR Kirchhoff stress, right? And we said the Kirchhoff stress can be written as J sigma, and we also observed that the first PLR Kirchhoff stress is not symmetric. There is another stress measure called the second PLR Kirchhoff stress. Second PLR Kirchhoff stress. But before we go to the second PLR Kirchhoff stress, we have to understand a very important operation called pullback and push forward operations. Though the mathematics behind pullback and push forward operation is slightly involved, because this comes from differential geometry, we will understand what we mean by this pullback and push forward operation, because that concept will help us also to understand what we mean by the second PLR Kirchhoff stress. Okay? So we will physically understand what it means, this pullback and push forward. It's very simple to understand that. And mathematically we will develop, not so very rigorously, but you may have to take some of the statements which I say, because it may be difficult for me to prove all the things, okay, right now, because the background what you have may not be sufficient to understand a few of the facts that I'm going to say. So let us look at what is pullback and push forward. What do you understand by the term, say, pullback? Okay, the setting is something like this. I have now the body at a reference coordinate or reference configuration, and that body is deformed. Okay, let me really deform the body. So that body might have really deformed. Okay, now there is definitely now a pullback and push forward that is possible between these two configurations. The x's belong to this, small x belongs to this, and so on. If you remember, we had two quantities, and we call this as a material, the spatial descriptions, and we had two quantities. For example, if you look at strain, we had a quantity E here, and we had a quantity capital E here, defined with respect to this, and with the E, small e defined with respect to the deformed configuration. Now, let us now look at the relationship between the two, the small e and capital E. Okay. Now, what is small e? If you remember, right, half into, no, that's small e, I minus F inverse transpose, F inverse is what we had seen as the, it's very good, so all of you are familiar now with the quantities. Okay. Now, that I can write it, for example, as F transpose half of F inverse transpose, okay, just multiplying by, or rather I'll do the other way, so it is easier, F inverse transpose because ultimately I want, you will just see why I want this. I want E there into I minus F inverse transpose F inverse, and I want F there, so I'll put F here and F inverse here. So what I've done essentially F transpose F inverse transpose F transpose, which is I, okay, this quantity, and then look at this quantity. So this can be written as F inverse transpose half of F transpose, that F I'm bringing it inside, F minus, when I multiply that, that will become I F inverse. So this you can recognize that as E, so that capital E rather, so that small e can be written as, look at this here, F inverse transpose E F inverse. Look at that expression there. What does it do? What does that operation does? What does this operation do? It pulls back E, this operation in the sense that F inverse post E and F inverse transpose pre E. Okay, what does it do? It pulls back this capital E, or the green strain, or rather pushes forward, pushes forward, okay, the capital E, which belongs to the reference configuration, to small e, which belongs to the current configuration. In other words, material configuration and spatial configuration. In other words, again, Lagrangian, Eulerian. Now, these are synonymous terms. So this is a kind of an operation which pushes forward E. Okay, this is called as the push forward operation. Okay, pullback is the inverse of this operation. Pullback is the inverse of the operation. So in other words, what the question is, what should I do like this in order that I can pull back E, which means that what is that quantity capital E, okay, how do I get that quantity capital E? By pulling back small e, because after all both of them have a relationship. Both of them are strains. Okay, one is referred in one coordinate, another is referred in another coordinate. So how do I now pull back small e so that I will get capital E like what I did here? Okay, let us see how you do that. Do this in a similar fashion. Okay, now, so what I do require in the left hand side is capital E. Okay, so capital E is equal to half into F transpose F minus I. So I need F inverse transpose F inverse. So what do? I multiply by F transpose F inverse transpose, so that will be half into F transpose F inverse transpose, okay, multiplied by F transpose F minus I into F inverse F. Rearranging this the same fashion as we did, bringing that 2 inside, okay, rearranging that, I will get F transpose E F. Right? This is called as the pullback operation, pullback of E. Yes, that's exactly, you could have got it. It doesn't matter, you could have got from here also. Okay, F inverse transpose, here multiply by F transpose, this will go off F, you will get this equation. So this is what is called as the pullback. Now, pullback and push forward operations, okay, are mathematical operations for the physical things what you had seen. I had talked about in words like we are referring to the reference coordinate, we are referring to current coordinate and so on. This is a mathematical expression. But unfortunately, these mathematical expressions is not the same for every tensor. In other words, it is not that if I give a quantity in the current coordinates, I can get a quantity, an equivalent quantity in the reference coordinate, okay, by applying, say, the pullback operation. Say, for example, we know sigma. We know sigma belongs to the current coordinates because of Cauchy stress. So it is not that if I take Cauchy stress and just apply this, okay, I will get an equivalent stress. An equivalent stress. There is a subtle difference between the way quantities like stress behaves and the quantities like strains behave. Okay, many of the strains, another one or two things, let's not worry about that, but more popular strains. Why is that? Do you have any idea why the stress doesn't behave in the same fashion? In the same fashion, why is it that the stress do not behave? The answer is very simple, because when I go to stress work, okay, stress work, say for example, you would have seen in your earlier classes on, say, virtual work, okay, virtual work. So in the virtual work, internal work is what we call as stress work. People call this with different names. What is it? Delta epsilon transpose sigma. So you have two terms there. So what are the two terms? Stress term and a strain term. Okay. So when you have these two terms, the stress term and the strain term, okay, one is the conjugate of the other. One is the conjugate of the other. Ultimately, when I calculate the stress power, whether I do that in the current coordinate or whether I do that in the reference coordinates, I should get the same stress power, right? So if I have, for example, the same transformations for the stress, then when I multiply that by sigma, in other words, delta epsilon transpose sigma, then I will not get, then F will enter into my stress term or stress power term, and I will not get the same value on two reference configurations. So in other words, stress is, that is what I called as the conjugate of the strain. This is similar to covariant and contravariant basis. Okay, we have not covered covariant and contravariant basis. These things behave like a covariant tensors, and the stresses which are conjugate of this, okay, is called as the contravariant tensors. But we will not go into these details. But let us now look at how quantity like stress behaves when we do a push forward or a pullback operation. Okay? The concept is very simple, as I told you, that we will look at stress power. So when I say stress power, actually we replace that epsilon by epsilon dot, or in other words, what we say delta D transpose sigma dV, the first term. Remember that this is the first term. Actually, this is small v because now it is in the deformed. This is the first term which you had seen in one of your earlier classes on virtual work principle. So now this is what we have to look at, okay, and see how this transformation takes place when I now convert this guy here to capital V. Is it clear? So the ensuing transformation will result in the transformation for stress. When I convert that to D capital V, then that will be the pullback transformation, okay, such that you will see now that the stress power is not affected by varying the coordinate system. or the reference coordinate, or whether it's the current coordinate system. Right? So the first step obviously is to replace this d small v by j d capital V. Okay, this in a vector notation is also written as sigma double dot delta d j dv. Okay. Now, what is this? Sigma ij, in fact, sigma being symmetric, sigma ij delta d ij. So, if you want to write this, sigma ij delta d ij j dv. Actually, I'm still not correct. I've done only the first step. What is the second step I have to do? I have to replace this quantity. What is this quantity d? I thought we had already, no. D yesterday we saw that, okay, right? I used the symbol d only, if I remember right. Please have a look at that. Yes. Rate of deformation tensor. What is that? That is the, what is the rate of deformation tensor? That is the symmetric part of L. Okay. Now, so rate of deformation tensor, being actually you can easily guess it because it's in small d, okay, is the one which comes from small l, and small l has grad v, small g grad v. That means that this quantity refers to the current coordinate system. So it is not enough if I just replace that by j d capital V. I have to replace as a next step this as well, okay, to the current coordinate, to the reference coordinate system. In other words, I have to express this in terms of what? E dot. Right. So what is the relationship between d and E dot? I think we had already seen that. D is equal to, no, D is equal to, so E is equal to E dot, we see F inverse transpose E dot F inverse. Okay. So what is delta D now? Delta D, obviously it goes to E dot, so F inverse transpose delta E dot F inverse. Now, let us see, you manipulate it and see, I give you 2 minutes, let us see whether you can manipulate this and get, that's going to be a very nice manipulation. Let us see how you do that. Okay, so that you will get E dot there and another quantity. So you will get two quantities. In other words, I'm giving you in a nutshell what answer I'm looking at. I'm looking at an answer where I will get one quantity which I can call as the pullback operations result, and another quantity which will be based on, okay, delta E dot. So let us see whether you can do that. So look at that. Okay, let me help you out. I want you to do this because that will give you a lot of confidence to do things, manipulations, because in nonlinear continuum mechanics as well as in finite element, a lot of things depend upon manipulations. You have to know how to do manipulation with this kind of tensor quantities. That's the reason why I feel that you should do it. In fact, most papers are rendered difficult because many of the simple manipulations you may not be able to derive unless you have some practice. Okay, so write this down. First step, let us write it down in the indical notation. Okay, let us see. Say delta dij. How will you write this down in an indical notation? So obviously, I should start with I and end with j. Okay, so in the middle I can write delta ik, delta E dot, say KL, F inverse Lj. So substituting it in sigma ij delta dij, okay. Of course, j is also there. J we will keep, we will reserve it, we will put it at the end. So this can be written as sigma ij f inverse transpose ik delta f dot kl f inverse lj. Is that clear? Delta f, not f dot, sorry, e dot. Okay, still you have to manipulate because I have to get that delta E dot outside. I should write delta E dot outside with another quantity here. Okay, so then only I will be able to get the stress. Let us see, let's do the next manipulation. Look at this. So this can be written as, of course, j, well, if I want I can add that j. Since sigma ij is equal to sigma ji, okay, I can replace that ij by ji, okay. Then I can write that as j sigma j I f inverse transpose ik, okay, delta E dot kl f inverse lj. That's the first step. In fact, since I put j and I, okay, then I can write that as j and that to be I. Or I can keep it as it is. Right, how do you further do that? Just try that out. Ultimately, you can write that quantity to be j f inverse, so you can bring sigma inside, f inverse sigma f inverse transpose delta colon delta E dot. Okay, by juggling this I and j, okay, you can keep juggling this so that ultimately you will get that will be the stress power integral of this V over dV. Now all of them are dummy here, that's all. What I made use of is that all of them are dummy because the result is a scalar. I and j, j and I, all of them are dummy. I can keep shifting that up and down 3 steps, then I will get that f inverse sigma j, sigma f inverse transpose delta E dot dV. Now look at this quantity. That quantity, okay, is the one which goes with delta E dot or the conjugate of delta E dot in order to give me stress power. Okay, so that quantity can be called as a stress. What is the physical meaning? There is no physical meaning to it. Okay, that quantity can be called as a stress, and that is called as the second PL of Kirchhoff stress. Yes. That is called as the second PL of Kirchhoff stress. Yes. So essentially what is that you have done? You have pulled back sigma, okay, sigma to the reference coordinate. You have pulled back sigma to the reference coordinate. Okay, so the pullback operation is slightly different now than what it was in the previous case. Okay, and the resulting stress is the second pk, Euler-Kirchhoff stress. The advantage of this is that, look at this, suppose I take the transpose of S, obviously then F inverse transpose becomes F inverse, sigma being equal to sigma transpose, so F inverse transpose, F inverse rather becomes F inverse transpose, so S is equal to S transpose, and hence second Euler-Kirchhoff stress is a symmetric stress tensor. It's a very important conclusion, that the second Euler-Kirchhoff stress is a symmetric tensor. Note this very carefully, another important point. Now I have defined casually 3 measures, stress measures. In fact, I can go on defining another 2 more. If need be, I'll do that later also. But note that it is not possible for me to pick one stress from the basket of stresses and another strains or strain rates from the basket of strain rates, and then say that for my problem I will use, say, second Euler-Kirchhoff stress, and I will use, say, E, small e, as the strain measure. It is not possible to do that. Okay? And you will see that there are conjugates for every stress or every strain. For example, if you see that if you take P, it has its conjugate, say F dot. In other words, what is conjugate? What we mean to say is that whatever be the stress measure and the strain measure we use, there should not be any change in the scalar. There should not be any change in the scalar. Okay? In fact, we arrived at second Euler-Kirchhoff stress from that concept. So we are totally wrong if I say that I will take sigma and I will take E and do my problem. This is not correct. They are not conjugate measures. Is that clear? So though you have a number of stress measures, number of strain measures, whenever you do a problem, you have to be careful in selecting one and the other such a fashion that they go together as far as this is concerned. Is that clear? Okay. Note the difference between this pullback operation and the pullback operation just we defined for E. What was the pullback operation which we defined for E? That was F transpose EF. Compare that with this. Okay, they are different. Okay, so we have defined the second Euler-Kirchhoff stress measure as well. So with that, we'll stop for a minute and do a couple of problems so that we become familiar with what all we are doing. Okay, we'll continue these problems in the next class as well, so that we have some exercise to manipulate and get certain results. So can you note down a problem? For a 2-dimensional problem, the deformation for a 2-dimensional problem, the deformation is given by the explicit equation x1 is equal to 4 minus 2x1 minus x2, and small x2 is equal to 2 plus 3 by 2 x1 minus half x2. Okay. Now determine the matrix representation of the deformation gradient. That's the first step. Determine the matrix representation of the deformation gradient. Also determine the inverse. Also determine the inverse. That means determine F and F inverse. I'm sure all of you know how to do F inverse of a matrix. And study the deformation of a square. okay, of a square, say formed by say vectors E1 and E2. In other words, tell me what happens to this square under this deformation, okay, which is the deformation that's where you can say that it's at 0. But before you do that, determine the elongation of a material line element small a0 given by 1 by root 2 comma minus 1 by root 2. Okay, so this means that it is in the reference, this reference coordinate, so it's something like that, right? Also determine the length of B, the original length of B rather, original length of B, where B is given by 1 comma 0. That means that B is in the deformed coordinate. So your first step is to find out F. Let us see what is F. I'll give you 2 minutes and then we will write down the result for F. Look at that, and then my first step is to write down F. So what do I do? Simple. Dou x1 by dou capital X1 is my F11, because I told you that we would write it in a matrix form. So dou x1 by dou capital X1, that gives me minus 2. Okay, so that becomes F11. Then dou x1 by dou capital X2, which is going to become F12. So that becomes minus 1. Then dou x2 by dou capital X1, dou x2 by dou capital X1 is equal to 3 by 2, and dou x2 by dou capital X2 minus 1 by 2. So in a matrix form, this can be written as minus 2, minus 1, 3 by 2, minus half. The first thing I want you to look at is it is not symmetric. So unfortunately, I have seen over the years many students making the mistake of just like that assuming that F is equal to F transpose. They are so used to symmetric matrices in their earlier mechanics, structural mechanics courses. K is symmetric, sigma is symmetric, epsilon is symmetric. So they think that every matrix that comes in continuum mechanics or structural mechanics is symmetric. Okay, see that. So to be very, very careful in it, because you would see that many formulations in nonlinear analysis would give you, will land you up in, I would say, not even give you, land you up in unsymmetric matrices. They have its own problems. The storages are going to be high. The time required to solve them is going to be high, and so on. So please note that. Now calculate the F inverse for this. Quite simple. Calculate the determinant and put that. Yes. Is it minus 1 by 4? Minus 1 by 5. Let's give some time. Let's see. Okay, minus 1 by 5. 2 by 5. Minus 3 by 5. Very good. Minus 4 by 5. Okay, fine. So that's that done. I have to find out what happens to A naught. How do I find that out? How do I find out what happens to A naught? Let us say that the A naught is now transformed into A. So how do I write A? A is equal to, correct. So F let's see what happens. Ultimately, I want you to find out, of course, the length of A naught. A naught, I'm sure you know that the length of A naught is what? One. Half plus half, 1. So what is the length of A? And see how you can calculate the vector A. This is what is F. That's all. No, there is nothing great in it. So that will be minus 3 by root 2 and y minus 2 minus 2, no, this is minus 2 and okay, plus 1 by root 2. So this is plus 1 by root 2 minus 2 1 by root 2. So minus 1 by root 2 and this one 3 by root 2, pardon, root 2. Shall I take your word? 3 into 2 by root 2 plus 1 by 2 into root 2. So 4 by root 2. 4, no, this is 4. So 2 by root 2. So root, right? Are we correct? Everything is fine? Yeah. Okay. Actually, this vector is not right. So if I have to keep this vector, then actually it is both of them are plus. Okay. Anyway, it does not matter. Okay. So that's the opposite direction. Minus is there. So what is the length? Length is A0 is 3 by root 2. Is that clear? Is it that? Just check that up. 1 by minus 1 by root 2 will become 1 by 2 half plus, no, this is not. It's very simple calculation. Minus 1 by root 2 whole squared plus root 2 whole squared whole thing power half. So this will become 1 by 2 plus 2 whole power half, right? So that is equal to 5 by 2 power half, right? So now apply for B, apply the same thing for B. For F, using F inverse, what happens to B? So what happens there? Now, by the way, before we proceed, let us look at this F. What is this type of transformation? Look at this F. F does not depend upon X. So this transformation is called as a homogeneous transformation. Very good. So this is a homogeneous transformation. That means the f that is to be applied is the same throughout the body, doesn't depend upon capital X1 and capital X2. And so this transformation is called homogeneous transformation. So calculate what happens to B. So that what's the answer? Minus 1 by 5 minus 1 by 5 into 1, 3. Right? So your answers are minus 1 by 5, 2 by 5, minus 3 by 5, and I think this is again, no, it's not correct, 4 by 5. It's not minus 4 by 5 because that minus will go, and that is 4 by 5. Okay? Be careful with your calculations. So it should be 4 by 5, not minus 4 by 5. Just check that up, your F inverse calculation. So ultimately, so you have to be in touch. Okay, simple things. So that is what I would call as a B0 is equal to minus 1 by 5, 1 and 3. And what's the length of that? The length of B0 is equal to 2 by 5 root of 2 by 5. So in other words, what it means is that a line element which is now currently of unit length was in fact root of 2 by 5, and vice versa for the other guy, where we had a unit length vector that takes 5 by 2 root of 5 by 2. Okay, that's the first step. Now how do you calculate now what happens to a square like this? Yes, exactly. So you calculate what happens to these vectors, okay, and then do this transformation. Please do that. It's very straightforward. And see what happens to the square, plot that square as well. I leave that to you. It's a very straight. Now that we have done this, that's not going to be very difficult. Okay, let's move to the next problem. Please take down the next problem. In the current configuration of a continuum body, a certain physical quantity, so whatever be the quantity, a certain physical quantity is given, in space and time. That physical quantity, say let me call that as x, a phi, space and time, is written as minus T inverse mod of x. Let me remove all these things. Okay, so whatever be the quantity, we are not worried about that. So note that the space is characterized by x, time is characterized by t. This quantity is defined at all places except the origin, which means that we do not define it at t is equal to 0 and at x is equal to 0, okay, because at that point they become infinity. So this quantity is defined all over the place. Now let an observer travel with a velocity v, which is given as x1 x3 into t e power t inverse e1 plus x2 x3 into t e power t inverse of that e2 plus x3 squared into t e power t inverse of it, E3. So an observer is moving with this velocity. Determine the spatial, of course, time derivative and the derivative or the rate of change with this observer will see as he moves with this velocity of v. Determine the spatial time derivative and determine the derivative of this quantity as seen by the observer who is moving with the velocity small v. So in other words, find the time rate of change of phi, okay, spatial as well as seen by the observer. Note that in this place the only difference between what you have seen before and what I have given now is that in the previous case, okay, when we did the theory, the particle was moving, or the line element with the material points that was moving. Here the small difference is that the observer is moving. Doesn't make any difference. In other words, what I simply asked is what is the material time derivative. Okay. Now look at your notes in the last class. So you will see that d phi by dt is what we are talking about, is equal to dou phi by dou t plus grad of phi dot v. Note that phi is with respect to grad small g, or this is dou phi by dou x you have to determine. So note that this guy here is also with respect to the current coordinate. Note that v is also with respect to current coordinate. You be very careful in that and see that this v, you look at these things here, x1, x2, x3, all these things are with respect to the current coordinates. Okay. So your job is now to find out this, take the dot product. That's all. Okay. Now why I gave this problem is because of the fact that many times not only in continuum mechanics, in the whole of analysis itself, we have to look at relative things. Okay. For example, if you are looking at crack growth in a body, okay, crack is growing like that, you can also imagine that sitting at the crack tip, you can imagine that the material particles are moving, okay, right across you. So these kind of relative things are very useful to study many complex problems. We'll talk more about that in the next class.